In this module, we're going to look at the structure of IP headers. I'm going to open up a trace file called ftp-download good. Now this is an FTP communication where someone is just downloading a file from a server. I am interested in the IP header, so I'm looking at packet number 1, and I've opened up the IP header by right mouse clicking and saying I wanted to expand the subtrees. Now as I look at the contents of the IP header, I'm also going to look at the hex window down below to see where each of these fields sits. The very first field in the IP header is the version number field, and I'm looking at IP version 4 traffic. Now that only takes 4 bits to create that value right there. It's only the first 4 bits, the first half byte that you see down in the hex portion. The next field is the header length field, and the header length field is done as a multiplier. It's a multiplier of 4 bytes. The value that's actually in this field is multiplied by 4 bytes to get the total header length value. It's the second half byte down here that is used for the header length field. So the header length value is 5, and Wireshark has multiplied that out times 4 to give us our header length of 20 bytes. In the section on filtering on IP traffic, I'll show you how to filter on unusual values in the header length field. Now we also have the differentiated services field, which used to be the precedence and type of service fields. But now it's the differentiated services fields, and it's defined in RFC 2474. And in this area we can differentiate services for network traffic based on the settings in here. The code point, the ECN capable transport information. ECN stands for Early Congestion Notification. And basically nodes, hosts, or endpoints can set these values, and routers can also set these values to say whether there's congestion along the wire. The first thing they have to do is they have to set this bit to 1 to say that they are capable of dealing with ECN style traffic, early congestion notification traffic, and then they put in an ECN value after that. The CE there stands for congestion experience. So basically you would have a system that would say, yes, I'm capable of this, and set this bit to a 1, and then they would say 1 here in the ECN CE field to say, I'm also experiencing congestion. Now the first field that you see there, the differentiated services code point field, is defined, the values that you can have in there are defined in RFCs 2597 and 2598. The values that are placed in this field basically give a probability classification. It's called a drop probability classification. And based on the numbers that are in there, we can tell whether there's a higher probability that traffic will be dropped in a heavily congested environment, or a lower probability that it will be dropped in a heavily congested environment. And you can refer back to RFCs 2597 and 2598 for more detail. The total length field gives us a length of not only the IP header, but the header that follows it and everything that follows it up to the point where valid data ends. So this packet appears to have a 20-byte IP header and then 28 bytes after that before any sort of padding would begin. The identification value is unique for every packet that's transmitted on the wire. Even if you see something like a DNS retransmission or something where a user sends a DNS query, doesn't get an answer, waits a second, and then sends a second DNS query to the same server, a duplicate query, we can look in the IP header and see that in fact they're different packets because each one separately went through the stack and had an IP header put on it separately. So they'll have a unique identification value for each of the packets. I'll close up the differentiated services field so we have a little more room. Now we have the flags bits. The first flag there is set. It's reserved. It's not set for anything at all. But the second bit is the don't fragment bit. And if it's set to 0, it means you're welcome to fragment. But if it's set to 1, it means don't fragment this. Now we're talking about IP fragmentation. The next bit is used in case this traffic is fragmented somewhere along the path to indicate that there are more fragments to come or there are no more fragments to come. If there are more fragments to come, this is a communication that had to be fragmented, then this bit set would be at 1. If there aren't any more fragments in the set, it will be set at 0. Or if the whole entire set is not fragmented, it will also still set at 0. The next field is the fragment offset field, so that if this communication was fragmented across multiple IP packets, this would tell us how to reassemble the communications. Basically, this is given to us in 8-byte increments as well. So if for some reason we saw the number 2 in there, we're actually talking about placing this data 16 bytes into the packet when it's reassembled. The time to live field used to always be talked about as if it was number of seconds, but in reality this is a hop count field. This sender is sending out data on the wire starting with a time to live value of 128. And when it gets through the first router along the path, this will be decremented down to 127 by the router. If a packet ever arrives at a router and the time to live value is at 0 already, then the router's got to discard that packet. Most likely you will see time to live values of 0 when you run traceroute on a network. Another thought about the time to live value comes when we see fragmentation occurring in IP communications. If my system were to send out a stream of data where the packets are way too large and they have to be fragmented, when the first fragment of the whole entire set is received at the far end of the communication, the destination host, they're going to look at the time to live value in that packet, and they are going to start counting down as if it's worth seconds. They'll keep counting down to make sure that the rest of the fragments of the set arrive before the time to live value is 0 in its system as it's calculating it. If we don't get all of the fragments of the set by the time that counter gets down to 0, then we have to send back an ICMP message saying that we had a reassembly timeout. Sorry, we lost a packet of the fragment set. And that's one of the ugly things about IP fragmentation. The next field indicates what's coming up next. After the IP header, what should we see? The value 06 or the value decimal 6 indicates that TCP is coming up next. The most common values that you will see in there are a decimal 6 indicating that the TCP header is coming up next, or the decimal value 17, which indicates that UDP is coming up next. The header checksum field follows, and that indicates whether the IP header checksum value is correct. If we open that up in Wireshark, you'll be able to see that it says good is true, bad is false. We'll work a little bit more with those when we go into the filtering section next. And then we finish it off with the source and the destination IP addresses. Now these are both unicast addresses, which means that they are addressed to a single device. If the destination IP header begins with the value 224 through 237 in the first byte, then it's a multicast address. We also have a broadcast, which would mean that the destination address would be 255.255.255.255, or we have a subnet broadcast, which is where we might see something like a 10.2.255.255. So these are the basic fields of the IP header. In the next section, we'll look at how to filter on IP traffic. We'll build a capture filter, we'll build a display filter, and then we'll work inside of the IP header to build filters based on the individual fields, and I'm even going to show you how to build a filter using this header checksum information. Now I'm going to show you, using the FTP download-good trace file, I'm going to show you how to build IP capture filters, IP display filters, and then how to create filters based on individual fields in the IP header or individual conditions, such as whether the IP header checksum is good or bad. So the first thing we'll do is we'll look at creating an IP capture filter. So I'll select the Capture Options button. And I was working with ARP before, and I'll get rid of that. I'll select the Capture Filters button, and you can see there's already one made for you, and it's that simple. In the area of capture filters, ARP, TCP, IP, those are commonly known filter strings. So we can just type in the letters in lowercase and it will work. So I'll apply that filter, and then once I start capturing, I will only see IP traffic. Now to do a display filter, all we have to do up in the filter window is type IP. Just like in the capture filter area, display filters are almost always much easier than capture filters, and this is a case where they're exactly the same. So if I select IP and apply, I'll only be seeing the packets in the trace that have IP headers. Now if there was any ARP traffic in the trace, I wouldn't see that because ARP traffic does not have an IP header. So I'll open up a trace and show you what that looks like. I'll clear this out, and I'm going to open up a trace called ARP-bootup. And in this trace we have two DHCP packets which do have IP headers, and we have several ARP packets that do not have IP headers. If I type in IP in the display field and hit enter, I'll only see the traffic that has IP headers in it. So I'll clear out that filter. Now we can also do filters based on the contents of the IP header, any one of the fields in the IP header. Typically the most common one that you'll probably make is an IP address filter. So for example, you want to know every time a packet goes out from the IP source of 0.0.0.0. That simply means that a system doesn't have an IP address yet. This system is talking to a DHCP server. So I'll right mouse click, say I want to prepare a filter based on the selected value, and there we can see IP source is equal to 0.0.0.0. And let me show you a common mistake that people make when they do IP address filters. I'm going to clear this out, and I'm going to open up the trace file ftp-download good. And in this case, perhaps I want to build a filter looking for traffic that is coming to or from 67.180.72.76. Instead of doing IP source, I would type in IP ADDR ==, and then put in that IP address, 67.180.72.76. So when I apply this filter, I should be able to capture all be able to look at all traffic that's to or from that IP address. Well, if I change my mind and decide I don't want to see any traffic to or from that IP address, I need to put an exclamation point at the beginning of the filter and apply it there. What's common is people will go through and instead of putting the exclamation point at the beginning, they'll do an exclamation point =, inside of the filter. Now I'm going to apply this, and it doesn't work the way they might expect it to. And the reason for that is that we're saying IP address not equal to 67.180.72.76. Well, there are two places where the IP address can sit. So if it doesn't work over here, we'll look over in this area. And unfortunately, the way this filter works, it's going to still show us traffic for 67.180.72.76. So just a reminder, when you're using the exclamation points, put them in front of the filter so that it'll work properly, the way you expect it to. I'll clear out that filter. And now I'm going to go through and just show you a couple other filters you can do. You could do a filter based on a total length value. By right mouse clicking and preparing the filter, it's got a total length of 48. That means there's a 20 byte IP header, and in this packet there's a 20 byte TCP header, and there happens to be 8 bytes of data that follow that. If I'm looking for larger packets, I could say I'm looking for IP header length, IP length values that are greater than, let's say, 120 bytes. I'll click apply. Now all of these packets must have a value in the total length field greater than 120 bytes. So that's a very nice filter to build. Another one might be in the flags area. I'll clear out this filter, and I'm going to close down the differentiated services field. Here's our flags field for fragmentation. We can build a filter saying we're looking for packets that are part of a fragment set, or we're looking for packets where the don't fragment bit is set. If I'm looking for packets that are part of a fragment set, but not the last packet, I can right mouse click, say I'm preparing a filter based on the selected value, and you can see in this particular situation, the more fragments bit is set to 0, which means there are no more fragments. If I want to get fragments of a set except for the last one of the set, where it would be set to 0, I can change that value to 1. I'll apply and see if I have any fragment sets in here, and I do not. I'll close up this area, minimize it. Time to live, maybe we want to look at a filter for time to live values that are 5 or less, something like that. That would indicate somebody may be running a traceroute operation on the network. Maybe I want to find IP packets that are not TCP sitting on top, so anything other than TCP. One of the ways would be to use this field and use the not condition on there. The other, of course, would be go up to the filter area and type exclamation point TCP. That would work as well. Now in the header checksum area, we have these two conditions down below that say good is true, bad is false. Now this is a good checksum, and I can highlight that line where it says good is true, right mouse click and say I want to prepare a filter based on the selected value. If I want to find bad checksums, I can look for the value 0 in that field, because it would not be good. It would be turned off, which means it's bad. And I can apply that to find any IP header checksums that are not good in the entire trace file. I'll clear that filter out, and then I'm just going to take you down to the IP addresses one more time. Because besides being able to right mouse click and create a filter based on an IP address, we can also use a greater than symbol and say that we want to get any IP addresses that are greater than, let's say, 67.180.0.0. Now I'm looking only in the source field. If I only want to capture traffic from systems that start out with 67.180.0.0 and only go up to 67.180.255.255, I'm going to add a second expression. So I'm going to add ampersand ampersand ip.src is less than 67.180.255.255. Remember, because I have the AND operation in the center there, the packets that come in have got to match this condition and they've got to match that condition. They've got to have an IP source address greater than 67.180.0.0, and they must have an IP source address that's less than 67.180.255.255. And when I apply that, I shouldn't see any traffic coming from this 128.121.136.217 address. So let's try it out. And there our filter appears to have worked. Very nice. Now you can get the master list of filters available for IP in a couple of places. The first place would be on the Wireshark web page. On the Wireshark web page, you can select Documentation, then scroll down to the Display Filter Reference area, click on the link, and we're interested in IP traffic. So I'll select the letter IP, or the letter I, excuse me. Scroll down a little bit, and there's IP, Internet Protocol. I'll click on that, and it will show me all of the field names that I can use for my filters. So there we see IP.addr, that means source or destination address. IP checksum, checksum bad or good, which we see, that's Boolean, that's either going to be a 1 or a 0. Here we have the entire differentiated services field, the whole entire set, or we can individually build a filter based on the congestion experienced bit, or the differentiated services code point bit, or the ECN event congestion notification transport bit. There's our IP.dst, which is our ipv4 address that we can put as a destination, or we can put a host name, a string, if we have names resolved on our system. We can also do filters based on the flags value, whether the don't fragment bit is set to on or off, more fragments on or off, IP fragments, etc. We also can build some filters based on some unusual conditions, such as IP fragment error, multiple tail fragments that's on or off, whether there's a fragment overlap. And that's where when we reassemble the fragments, we see that one of these fragments is actually being placed right over where a previous fragment was, part of it or the whole entire thing. And then if it's different data, we would call that an overlap conflict. Or a fragment is too long. So we've got too much in there for a fragment. The numbers don't match when we add up the length values. There's our IP header length value, as well as the IP length value. That's the total length, including the IP header and any valid data that follows it. IP proto is what we could search on based on the protocol that follows the IP header. There's our IP source, which is an IPv4 address, and there's our string, which is based on a host name. There's our time to live value as well. So that may be one that you'll use to find traceroute running on the network. An additional resource for IP display filter values can be found in the expressions area. I'll click on the expressions button, and then I'll type in IP, and it will take me right down to the IP header area. I'll open this up, and there are the values that we just saw on that last screen. If I wanted to build a filter based on the IP total length, I could say it's equal to a certain value, or not equal to, greater than, less than, greater than or equal to, or less than or equal to, and put a value into this right-hand side position. So there are several filters that you can build for IP traffic. Remember that you have two basic sources. You have the wireshark.org website, and you also have the expressions area that's inside of Wireshark. In normal IP traffic, first of all, we would see packets going from one unicast address to another unicast address, or we might see packets going from a unicast address to a multicast address, but we should never see packets coming from a multicast address. We might also see packets going from a unicast address to a broadcast address. Again, we shouldn't see anything come from a broadcast address. If everything goes well when we look at the IP header, we should see the IP version 4 for IP version 4 traffic. The header length is typically going to be 20 bytes long because we really don't use the IP header options information much. In the total length field, we should be able to add that up and define that this includes the IP header plus any header that follows it and valid data. And we shouldn't see anything after the valid data. If there's padding required, it should be just junk in there. We shouldn't be able to read anything in the padding area. In addition, every packet that's sent out through the IP stack should have a unique identification number. We shouldn't see packets going out from the same identification number over and over and over on the cabling system. That would be different. In the area of fragmentation, I'll tell you, I don't like fragmentation. I don't like to see it on the cabling system. So it's okay if we see the don't fragment bit set on or off, but I'd like to not see more fragments on. In addition, the protocol field should show us what's coming up next, and the header checksum value should be correct. Now, we should recognize the source address if it's traffic coming from inside of our network. It should be one of our internal addresses. We shouldn't see anything coming from addresses that are outside of our network. That shouldn't be the source address field from the inside. Now, if everything goes well and this packet gets to the target system and the target responds, we should just see that the source and destination IP address fields are flipped and everything should look nice. Now I'm going to show you a series of trace files that have strange IP communications. The first one that we're going to open up is called pingfrag. Now in this communication we have fragmented IP communications, and unless for some reason we need to have fragmenting on the cabling system, I wouldn't expect to see it. These first three packets are part of a fragment set. So in the first packet, if we look inside of it, we can see there's our flags area with information about fragmentation. I'll bring this window up just a little bit more so we can see the fragment offset area. So in here, the don't fragment bit is not set, which means we're allowed to fragment, and there are more fragments to come. This is the first packet of the fragment set. The first packet of the fragment set will always have the more fragments bit set on and the fragment offset value to 0. The second packet in this set says there are more fragments to come, and this is where this packet should be placed in the fragment set. And then the final packet of the set, there are no more fragments to come. This bit is set to off, and the fragment offset field shows us that this is the third and final packet, and it should be placed at 2960 bytes into the frames. Now, I don't like to see fragmentation on the wire unless, of course, for some reason you really need to have fragmentation. So in this case, we have someone doing an ICMP echo request, and they're sending out so much data in that single ping packet that it can't go out onto the cabling system as is. It has to be fragmented. So it's a strange communication to see. I'll show you an interesting filter that you can build to locate fragments, all the fragments in a fragment set. The interesting fields in here would be, and I'll click on packet number 2, we can see that the starting fragments in a fragment set will always have the more fragments bit set on. But the last fragment in a fragment set will not have that on. It should be set off, which indicates there are no more fragments. But what that packet will have, which is unique, is it will have the fragment offset value not equal to 0. So those are the two values that I'll use to build this filter. Number 1, I'll go up to this packet just above it, and I'm looking for the more fragments bit to be set on. I'll right mouse click, prepare a filter based on this selected value. And then anytime we see a packet and it has a fragment offset value greater than 0, that packet is part of a fragment set. So I will select this field, right mouse click, and prepare as a filter. And I'm going to say or not selected, and I'm going to change the value to 0. So that means I'm interested in packets that have the more fragment bit set on, because we know that those are part of fragment sets, or any packet that has the IP fragment offset not equal to 0, because that's always going to be the last packet of the fragment set. I'll apply this, and if I apply this in this trace, every single packet should match. I'll apply, and sure enough, all 6 packets that were in there match my display filter, and that's good. Now the next trace I'm going to show you is an interesting one that I gathered at a trade show. So I'll open up a trace file. This one is called 127guy.pcap. Now I'm not seeing anything because I still have my filter up there, so I'll clear it out. It's not tough to see what's going wrong in this trace. We have a packet going out from 127.0.0.1 going out to the broadcast address. And nobody's allowed to talk from 127.0.0.1 on the cabling system. That's the loopback address. Not only do we have one packet, we've got a whole bunch of these packets going out, not at a very steady rate though. But the other interesting thing is that if you look at these packets and you focus on the Ethernet header value here inside of the frames, you'll see that they're not all from the same machine. Packet number 2 comes from a different system. Packet number 3 comes from a different system. Packet number 4, 5, 6. Every single one of these comes from a different MAC address. And if I select Statistics, Conversations, there are all the MAC addresses that I see in this traffic. So that's very strange, and you should never see that on the cabling system. This just happened to be an alpha product that was at a trade show that unfortunately had a pretty ugly bug in it. The next trace that I'm going to show you has to do with the identification field values. First of all, let me bring up a trace file so I can show you how the ID field normally increments in communications. So I'm going to bring up a trace file called FTP download good. Now this is an FTP communication. Everything went well. And we want to focus on the IP header ID value that this source here is using in its communications. So I'll build a filter on all traffic from this source IP address by doing a right mouse click, saying prepare a filter based on the selected value. And the only reason I do prepare a filter instead of apply right away is so that I can show you what the filter looks like. So this is my filter and I'll apply it. Now I'm looking only at one side of the conversation. Here's the first packet that was sent out from that system, and we can see the identification field value is 34,233. The next packet sent out from that system is 34,234. And the next packet is 34,235. And the next one is 34,236. So that's normal. That's what we would normally see. Let's go to the other side of that communication. I'm going to do an exclamation point saying that the source is not 67.180.72.76. Now we see the other side of the conversation. Here is the first packet from the FTP server. The ID field value is 42,145. The next packet counts up by 1, 42,146, and we keep incrementing as we go through. Now, not every TCP/IP stack is going to increment just by 1 for every packet, but it should increment. The number should be higher, not lower, and it should increment by at least 1. In the trace file I'm going to open up now, you will see problems with that IP header ID value. The trace file is called ettercap check for poisoner. And ettercap is a man-in-the-middle attack tool. I'm going to clear out my filter there. It's a man-in-the-middle attack tool. And it has a way of checking for other systems that might also be running ettercap. And the way it does that is it sends out an echo request packet, a ping packet, and it puts a specific value in the IP header's ID field. This is the value that it places in there. E77E, which is elite speak for short for ettercap, ETTE. And instead of incrementing with each one of these ping requests that goes out, it stays at the same value. Every single one of these packets has that same value. And when it gets an ICMP echo reply that comes back with that same value, it knows that it's found another ettercapper. So it's not typical to see the same value over and over again. And you should be aware that E77E is the signature of an ettercap device. The next trace I'm going to open up is called TTL counting. And in this case, it looks like we just have a series of pings going on the cabling system from one host to another host. In the IP header area here, though, I'm going to close some of these fields down. The first packet that we see going out from 10.0.0.29 goes out to 10.0.0.2. The time to live value is only set to 1, and that's unusual to see a low time to live value like that. We see a ping response come back, and the responder sets the time to live value for itself at 128. But this 10.0.0.29 sends out another packet with a time to live of 2. And the next time it sends a ping packet, it's at a time to live of 3. And the next time it sends one, it's at 4. This is typically seen as a trace route. What 10.0.0.29 is trying to figure out is the address of the routers along a path. Because if the target is off of this network, the packet will go to the router to be forwarded, and the router would never accept a packet coming in with a time to live of 1 and forward it on. The router can't decrement the time to live value to 0 and forward it on. So this would cause the router to send back a message saying, I'm sorry, the time to live was exceeded in transit. And that's the way this device would learn the first router along the path. And then the next packet would go out with a time to live of 2, and it would make it through the first router, and the second router would complain. So this device would learn the second router along a path. So anytime you see that time to live value counting up, 1, 2, 3, 4, 5, that's usually a trace route operation using time to live. The next trace I'm going to open up is called ugly trace. And ugly trace, when we look at it, seems very strange because it appears like we have duplicates all over the place. We've got this device sending out a reset and another reset. And then we see a SYN and a SYN, and a reset and a reset, and a SYN and a SYN. It seems like as we look through the trace, we've got everything duplicated in there. Now, that's not normal. A system shouldn't send multiples of anything out on the cabling system. We also see up here at the top, we've got a duplicate that starts it all out. So we're going to look a little more carefully at one of these duplicate sets. I'm going to bring this window up so we can see a little bit more information. Now, we know what the IP header value is because we can see it up here in the summary line. But what we don't know is what the Ethernet value is. So here, in packet number 5, and I'm going to turn off colorization here. Whew, it's just a little too much in that trace. In packet number 5, we see the source Ethernet address ends in an 80, and it appears to be going to a Cisco box that ends in 54. The second packet, the one that's a duplicate, comes from a Cisco interface that ends in A8 and goes to the system that ends in 80. Now, the interesting thing here, these are two different systems, I should tell you. One is this ambit 80 is the first sender, and then the runtop 80 is the second destination. So because these are going to a Cisco box and from a Cisco box, it feels like this is something called local routing. Local routing is when we want to send a packet to another machine on the same network that we're on, but we're all confused and our subnet masks are set incorrectly and things like that. So we send it instead to a router, thinking we're trying to get off of our network. And the router turns around and routes it right back onto our own network. We can tell if that's the case because we have the MAC headers changing with each of the packets. Other than that, they are the same packet. We should see the IP header ID field being the same, and it is between these two packets. But we would look at the time to live value and see if it's been decremented by 1. If so, the packet's been routed. Packet number 5 has a time to live value of 128, and packet number 6 has a time to live value of 127. So sure enough, we have this nasty process of local routing. And we look at the source of the packets as the device that we need to go fix. The next trace I will show you is an IP scan. The trace is called nmap-ipscan.pcap. In this trace, someone is using nmap to find out what services sit on a target system directly above IP. Now, there are a number of services that could sit directly after the IP header. We're most familiar with TCP and UDP, but we also have EGP, as you can see here from this trace, TLSP. These are all different communications that can reside right after the IP header. For example, ICMP. ICMP packets sit right on top of the IP header. We have no TCP and no UDP header involved. So this scan is going on the cabling system to try to identify what protocols are sitting right after IP. Most likely, they're trying to find a router on the network, and that's abnormal communications. I'd highly recommend at this point that you baseline your own network communications. Look and see how many multicast packets you have, the level of broadcast traffic that you have. Look at your typical time to live values. Get familiar with how your network looks when you do an analysis of it. Do you have any fragmentation on your network? Once you have that baseline, it'll be great when you come to the day and you have to troubleshoot that network and you have something to compare it to.